What if the strangest thing about our universe is not that it exists, but that it seems almost suspiciously well suited for existence? Change gravity slightly and stars might never form. Alter the strength of electromagnetism and chemistry could collapse. Shift the balance of the forces inside atomic nuclei, and the elements needed for planets, oceans, and living cells might never appear. Even the amount of dark energy in empty space seems to sit inside a narrow range that allows galaxies to survive long enough for observers like us to emerge. So why does the universe look this way? Did the laws of nature somehow have to be exactly what they are? Are we seeing evidence of a deeper mathematical principle that physicists have not yet discovered? Or are we making a far more unsettling mistake, assuming that our universe is the only universe there is? This question has haunted physics for decades, and Leonard Susskind became one of the central figures in a scientific argument that challenged the way many physicists had hoped reality would work. For much of the 20th century, physics seemed to be moving toward an elegant dream. Nature, researchers hoped, would eventually reveal one unique mathematical structure beneath everything, a final theory, one unavoidable set of equations from which the masses of particles, the strengths of forces, the number of dimensions, and perhaps even the history of the cosmos could be derived. Einstein spent much of his later life searching for a unified description of nature. Generations after him carried that ambition forward. The dream was not merely to describe the universe, but to explain why the universe could not have been different. Then something deeply inconvenient happened. The deeper physicists looked, the more the laws of nature began to resemble a collection of adjustable settings. Consider the electron. It has a particular mass and charge. Quarks have their own masses. The forces of nature have specific strengths. Space appears to contain a small amount of vacuum energy. The standard model of particle physics describes many of these quantities extraordinarily well, but it does not tell us, at least in its current form, why all of their measured values are what they are. They are simply parameters that must be obtained from experiment. Imagine discovering an incredibly complicated machine filled with hundreds of knobs. You understand how the machine works once the knobs have been set, but nothing in your instruction manual explains why they were turned to those exact positions. That is roughly the discomfort physicists face. And some settings appear strangely important for complexity. This does not mean that every popular claim about cosmic fine-tuning is correct. Scientists disagree about how narrow some life-permitting ranges truly are, and we do not know every possible form that complexity or life might take under different physics. But several puzzles are real, and one in particular became impossible to ignore: the cosmological constant. Einstein first introduced the cosmological constant into general relativity as a way of keeping the universe static. After astronomers discovered that the universe is expanding, he abandoned the original motivation for it. Decades later, the idea returned in a much stranger form. In 1998, observations of distant exploding stars revealed that the expansion of the universe is accelerating. Something appears to be pushing space apart. We call the dominant cause dark energy, and the simplest explanation consistent with current observations is a cosmological constant, a constant energy density associated with empty space itself. The value is extremely small in the natural units used by particle physicists. That creates an enormous theoretical puzzle. Quantum field theory suggests that empty space is not truly empty. Fields fluctuate. Virtual processes contribute energy. Naive calculations of vacuum energy can produce values catastrophically larger than what astronomers observe. The disagreement is so extreme that it has often been described as one of the worst prediction problems in theoretical physics. But there is another side to the mystery. If the cosmological constant were much larger and positive, the universe could have expanded too rapidly for matter to gather into large galaxies. Without galaxies, there may have been no long-lived stars, no heavy element-rich planetary systems, and no observers asking why the universe appears finely balanced. This is where a once controversial idea entered modern cosmology, the anthropic principle. The name can be misleading. It does not mean that the universe was created for humans. It does not claim that humanity occupies a privileged cosmic position. In its cautious scientific form, it says something simpler. Any observation we make is necessarily conditioned by the fact that we exist in a region of reality compatible with observers. Suppose a person wakes up inside a room with breathable air. They should not be shocked that the air is breathable in exactly the same way they would be shocked if a random room chosen from all possible environments happened to contain perfect conditions for human survival. The fact that they are alive already filters the possible rooms in which they could find themselves. The logic becomes powerful only if nature provides many different environments. One universe with one unexplained cosmological constant does not solve anything, but millions, or vastly more, universes with different values might. And this possibility brought Leonard Susskind into one of the most intense conceptual battles in modern theoretical physics. Susskind had already spent decades at the center of revolutionary ideas. He was one of the founders of string theory. He played a crucial role in the development of the holographic principle and in the long-running debate over whether information is destroyed by black holes. By the early 21st century, he began arguing that string theory itself might contain a clue to the apparent fine-tuning of nature. The clue was something many physicists initially viewed as a disaster. String theory does not obviously produce one unique universe. It appears to allow an enormous number of possible vacuum states. To understand why, imagine that the equations describing fundamental physics are not instructions for constructing one house. Instead, they describe a gigantic landscape containing valleys, hills, plateaus, and depressions. Each valley represents a possible stable or long-lived configuration of the underlying theory. In one valley, particles may have certain masses. In another, the forces may have different strengths. Some valleys may correspond to worlds with different low-energy physics. The full mathematical situation is enormously complicated, and scientists still debate what parts of this picture are fully controlled. But the central possibility became famous as the string theory landscape, and Susskind embraced its implications more strongly than many of his colleagues. If string theory contains a vast number of possible vacuum states, then perhaps the constants of nature are not uniquely determined because there is no unique answer. Perhaps different regions of a much larger cosmos realize different physical possibilities. That idea sounds almost like science fiction, until inflation enters the story. Inflation is a leading cosmological framework proposed to explain features of the early universe, including why the observable cosmos is so large, smooth, and nearly spatially flat, while also providing a mechanism for generating the primordial fluctuations that later grew into galaxies. Inflation itself is not a single finished theory. There are many models, and important details remain under investigation. But some inflationary models have a remarkable property. Inflation may become eternal. Not eternal in the sense that our local universe expands forever, but eternal because while inflation ends in some regions, it continues in others. Imagine boiling water except in reverse. Instead of bubbles forming inside ordinary water, regions where inflation ends form like bubbles inside a background that keeps inflating. Each bubble can grow into a universe-sized region. The process may continue without ending globally. If different bubbles settle into different vacuum states allowed by fundamental physics, then the universe we observe could be only one member of an enormous multiverse. Suddenly, the strange settings on nature's control panel have a possible explanation. They were not selected specifically for us. We are here because only certain settings permit anything capable of asking the question. This is the heart of the anthropic landscape that Susskind helped popularize, and it horrified some physicists. The problem was not that the idea sounded strange. Modern physics is filled with strange ideas. Quantum mechanics allows particles to exist in superpositions. General relativity turns gravity into curved space-time. Black holes hide regions behind horizons. Strangeness alone is not a scientific objection. The deeper concern was predictability. If nearly every possible set of constants occurs somewhere in a multiverse, what does physics actually predict? A theory that explains anything after the fact may risk predicting nothing before the fact. For physicists who had spent their careers searching for a unique, inevitable theory of nature, the landscape felt like surrender. They wanted an equation that would say the cosmological constant must equal the number we observe. The anthropic view offered something very different. It suggested that the value might vary, and that observers naturally find themselves only where the value permits galaxies and complexity. The philosophical discomfort was enormous, but then came a historical detail that changed the debate. Before the discovery of cosmic acceleration, physicist Steven Weinberg had used anthropic reasoning to estimate an upper bound on the cosmological constant based on the requirement that galaxies be able to form. His reasoning did not predict the exact measured value. The assumptions were simplified, and the subject remains technically complex. But the fact that the observed cosmological constant later fell within an anthropically interesting range attracted enormous attention. To supporters of the multiverse, this was not proof, but it was a warning. Perhaps anthropic reasoning could sometimes make scientifically meaningful statements. Susskind pushed further. To him, the cosmological constant problem suggested that physicists should take environmental explanations seriously. Consider an analogy. For centuries, someone might have tried to derive Earth's distance from the Sun from fundamental mathematics. Why exactly this distance? Why not closer? Why not farther? Today we know that planets form at many distances around many stars. Earth's orbit is not a universal constant. It is an environmental fact. Our planet lies where liquid water can exist partly because otherwise we would not be standing here discussing astronomy. Perhaps, Susskind argued, some quantities physicists had assumed were fundamental could be more like planetary geography, not laws, locations. The thought is revolutionary because it changes the question. Instead of asking, why does nature choose these constants? We might ask, why do observers find themselves in regions with these constants? Yet immediately another mystery appears. How many universes are there? The answer, often associated with string theory, is staggering. Researchers have discussed landscape estimates involving numbers such as 10 to the power of hundreds or even 10 to the power of 500 possible vacua. These should not be treated as a precise inventory of universes. They are order of magnitude indications of how enormous the space of theoretical possibilities might be under certain constructions. 10 to the 500 is a number beyond ordinary imagination. There are nowhere near that many particles in the observable universe. If reality can realize even a small fraction of such possibilities, almost every physical environment we can meaningfully distinguish might exist somewhere. But now the multiverse creates its own crisis. Probability. If eternal inflation generates infinitely many regions, how do we calculate what a typical observer should see? Infinity divided by infinity is not a probability. Different ways of counting universes can produce different answers. This is known as the measure problem, and it remains unresolved. The multiverse does not simply erase fine-tuning and walk away victorious. It replaces one mystery with several others. What counts as a universe? How should different regions be weighted? Which vacuum states are actually stable enough to exist? How are observers defined? And perhaps most importantly, can any of this be tested? The question of testability sits at the center of the controversy. We cannot currently travel outside our observable universe and inspect other cosmic bubbles. If other regions are permanently beyond our horizon, direct detection may be impossible. Supporters of landscape reasoning argue that indirect scientific tests are still conceivable. A theory can gain credibility if the framework generating the multiverse independently predicts observable features of our universe. Some cosmological models might also leave signatures associated with bubble collisions, although no convincing evidence for such events has been established. Critics answer that unless the theory produces sufficiently sharp predictions, the multiverse can become too flexible. This debate is not finished, and that matters. The landscape should not be presented as an established discovery. There is no observational proof that a string landscape multiverse exists. String theory itself remains a theoretical framework without direct experimental confirmation at the fundamental scale. Eternal inflation is possible in many models, but we do not know whether our universe arose from an eternally inflating background. The anthropic explanation of constants is therefore a serious scientific proposal, not a settled fact. But the puzzle it attempts to address is very real. And the puzzle becomes stranger when we look beyond dark energy. Carbon, for example, plays a central role in known biology because of its unusual chemical flexibility. Inside stars, carbon is produced through nuclear reactions involving helium. The process is enhanced by a particular excited energy state in the carbon-12 nucleus known as the Hoyle state, predicted by Fred Hoyle before it was experimentally confirmed. This story is often invoked in discussions of fine-tuning, but it requires caution. The existence of carbon depends on nuclear physics, Yet modern calculations suggest that stellar production of carbon and oxygen may remain viable over a wider parameter range than simplistic popular accounts sometimes imply. Nature may be tuned, but not necessarily as delicately as every dramatic claim suggests. The deeper question survives anyway. Why do stable atoms exist at all? Why are there long-lived stars? Why can matter organize itself into structures vastly more complicated than the laws needed to describe it? And why does mathematics capture those laws with such extraordinary precision? The multiverse may explain why we observe certain constants, but it does not explain why there is a landscape in the first place. It simply pushes the question deeper. Why string theory? Why quantum mechanics? Why any underlying law capable of generating universes? Even if every possible vacuum exists, why does possibility have structure? This is where physics approaches the edge of philosophy without necessarily crossing out of science. Susskind's position has often been associated with a willingness to abandon the demand that every feature of nature must have a unique fundamental explanation. That may sound disappointing, but history has forced physics to abandon similar intuitions before. Kepler searched for deep geometric reasons behind the distances of the planets, trying to connect their orbits to perfect Platonic solids. It was beautiful. It was wrong. Planetary distances emerged from the contingent history of solar system formation. Perhaps physicists, searching for a unique derivation of every particle mass, are making a more sophisticated version of Kepler's mistake. Or perhaps not. Perhaps beneath the apparent landscape lies a deeper principle that really does select one universe. No experiment has yet decided the question. And there is another possibility, more subtle than either design or multiverse. Maybe the universe only looks improbable because we do not yet understand the space of possible physical laws. Imagine drawing one card from a deck and receiving the ace of spades. If you believe there are trillions of equally likely cards, the result looks miraculous. But if you later discover the deck contained only the ace of spades, the miracle disappears. Fine-tuning arguments depend not only on measured constants but on assumptions about which alternatives are physically possible and how likely those alternatives are. We do not know that distribution. Physics currently has no universally accepted probability measure over all conceivable laws of nature. So when someone says that our universe is unimaginably unlikely, the honest response is to ask, unlikely compared with what? That question does not erase fine-tuning. It reveals how incomplete our understanding still is. The universe may be selected from a landscape. It may emerge uniquely from mathematics. It may arise through principles we have not discovered. Or the distinction between necessity and accident may itself turn out to be too primitive for the deeper theory. Yet from our tiny planetary perspective, reality continues to offer one astonishing fact. The universe did not merely produce matter. It produced matter capable of looking back at the universe. Hydrogen formed stars. Stars forged heavier elements. Those elements became planets. On at least one planet, chemistry became biology. Biology became nervous systems. And nervous systems eventually became physicists, wondering why the constants of nature allowed physicists to exist. There is a strange circularity to it. We use the fact of our existence as evidence about the universe that produced us. The observer becomes part of the observation. Quantum physics had already taught us that observation cannot always be treated as philosophically trivial. Cosmology adds an even larger complication. There is no external laboratory from which we can observe the universe as a whole. We are inside the system we are trying to explain. Every telescope, detector, equation, and theory is a product of the same cosmic laws under investigation. That does not make science objective. It makes selection effects unavoidable. And perhaps that is Susskind's deepest challenge to traditional expectations. The laws we observe may not all be universal necessities. Some may be cosmic accidents filtered by existence itself. If that is correct, then the apparent design of the universe is not evidence that the cosmos was arranged for us. It is evidence that we could only awaken in the rare kind of place where awakening was possible. But there is something almost more disturbing about that answer. Because once the multiverse explains why our universe appears habitable, we are left staring at the mechanism that supposedly creates the multiverse. A quantum framework, an inflating space-time, a landscape of possible vacua, mathematical laws capable of generating complexity. And suddenly the original mystery returns at a higher level. Why does that structure exist? Why is there a reality capable of exploring possibilities at all? We can imagine replacing one finely tuned universe with an enormous cosmic lottery. But a lottery still needs rules. It needs a space of outcomes. It needs something that determines which outcomes are possible. And no matter how far physics pushes the explanation backward, eventually we confront a question that may be either the deepest scientific problem imaginable or a sign that human intuition has reached a place it was never evolved to understand. If our universe is only one habitable valley inside an almost endless landscape of possible realities, then perhaps the most extraordinary thing is not that our universe looks designed. Perhaps the extraordinary thing is that existence has a landscape in which anything can exist at all. And if the laws of nature themselves are only one layer of a deeper structure, what exactly are we looking for when we ask why reality is the way it is?